The primary objective of herbicide use is to optimise weed kill, and a pre-emergent herbicide's effectiveness will be influenced by a number of key factors: tillage or no-till, stubble cover and spray application, herbicide solubility, herbicide binding, and incorporation by sowing. Have weed seed beds been disturbed by cultivation, or is there a no-till farming system in place? Depending on the herbicide chosen, no-till systems may provide improved weed control, as the weed seeds are likely to be close to soil surface where the herbicide may be most concentrated. On the other hand, tillage buries weed seeds at a range of depths and reduces the herbicide concentration around the weed seeds, particularly if using low-soluble herbicides that are not mechanically incorporated. Burial of weed seeds by tillage also results in increased seed bank dormancy and, for some weed species, a higher level of multiple germinations. Seed burial also reduces seed mortality rates in many weed species. A farming system based on tillage will prolong the life of the weed seed bank for a number of weed species, hindering efforts to reduce the seed bank. Is there much stubble, and how even is the coverage? Stubble will intercept and bind several pre-emergent herbicides, which in turn reduces the amount getting to the soil surface and impacts weed kill efficacy. Trifluralin binds very tightly to stubble and is unlikely to be washed off with following rainfall. However, trifluralin can still deliver useful weed control in no-till systems in the presence of moderate stubble levels. This is provided the stubble is standing and attention is applied to the spray application to maximise the amount of herbicide reaching the soil.
Yeah, we've done a fair amount of work looking at percent of residue cover rather than like tons per hectare, but rather cover, and there's almost a direct correlation between how much cover there is on the surface versus how much herbicide is intercepted. So for example, if you have 30% cover, about 30% of the herbicide that you apply will be intercepted by the stubble. And that will show a fairly linear response up to about 80 or 90% cover. And then beyond that, it really doesn't change much, but you'll still get 80 to 90% of the herbicide will actually get intercepted by the stubble and will not reach the ground, at least not immediately.
There are a number of practical steps that growers can take to maximise spray deposition on the soil. They are spray and wind direction, travel speed, droplet size and water rates, nozzle angle and spacing, and boom height. You should operate your sprayer parallel to the stubble lines, ideally with a cross breeze to move spray into the stubble line. Slow down a little. Droplets exit the nozzle with forward momentum in the direction of travel of the boom, as well as downward momentum due to the speed and direction they leave the nozzle. Droplets with higher forward movement are more likely to be intercepted on the leading edge of the stubble or existing weeds, leaving an untreated shadow behind the weed or stubble. Reducing boom speed reduces the forward momentum of droplets, enabling more even soil coverage behind obstructions. Travel speeds of less than 20 kilometres an hour are advised, with speeds of less than 16 kilometres an hour advised in heavier canopy or stubble situations. The nozzle angle can also be changed by tilting the nozzles backwards 10 or 15 degrees. This counteracts the forward droplet momentum and results in droplets that leave the nozzle with a trajectory that's closer to straight down at 90-degree angle to the soil surface. Aim for a high quantity of large droplets, ideally travelling straight down as they leave the spray boom. This means coarse or very coarse droplets with water rates increasing as stubble levels increase. Small droplets should not be used as they are far more likely to be intercepted by an upright catching surfaces such as stubble, and far less likely than a larger droplet to shatter on impact. When a larger droplet shatters, some of the resulting droplets may eventually wind up on the soil surface. Coarse droplets are significantly better when trying to punch droplets down through stubble or a crop canopy to the soil surface, and solid droplets are more likely to reach the soil surface than slower-moving, air-filled droplets created by air induction nozzles. As a rule of thumb, use approximately 60 litres a hectare spray volume in situations of no stubble cover, 80 litres a hectare in light standing stubble, and 100 litres plus per hectare with moderate levels of standing stubble. Many broadacre booms are set up with 110-degree nozzles at 50 centimetre spacings. However, using narrower spray angle nozzles, that is, nozzles with a 65 or 80-degree fan angles, will generate faster droplet speeds and larger droplets, and importantly with a higher proportion of droplets travelling closer to the vertical than standard wider angle 110-degree nozzles. Narrowing the fan angle will lead to less stubble or canopy interception and help to achieve droplet coverage on the soil surface. Spray booms with closer nozzle spacing, for example 25 centimetres, will generally give better coverage than wider 50 centimetre spacing. Keep your boom height as low as possible, while still maintaining double overlap at the target. For 110-degree nozzles, this should be approximately 50 centimetres above the top of the standing stubble, and for 65-degree nozzles, 90 centimetres. Higher boom height means that the droplets have further to fall before reaching the target. This increases the risk of off-target drift, and also increases the droplet exposure to evaporation, which can further reduce droplet size as it falls to the target. This is particularly important in hot and or low humidity application conditions. Increasing the boom height from 50 to 70 centimetres above the target typically increases the risk of drift by 4 times. Moving from 50 centimetres to 100 centimetres above the target may increase the drift risk by 10 times. To obtain great coverage and maintain low boom height, you could double nozzle number by halving nozzle spacing to 25 centimetres. Solubility is about how much of the herbicide dissolves in water and how herbicides move through the soil profile after rain. Herbicides have a wide range of solubility. DNA herbicides such as trifluralin and pendimethalin have very low solubility and generally are difficult to move through the soil with rainfall. Peroxysulfone, trialate, propyzamide and prosulfocarb are considered to be of low solubility. However, they generally have enough solubility to be able to be washed off stubble and into soil following adequate rainfall. S-metolachlor has moderate to high solubility, being easily able to move into the soil following small rainfall events. Group B herbicides such as trisulfuron and chlorsulfuron are highly soluble and will want to remain in the soil moisture, moving wherever the soil moisture moves. Herbicides with high solubility can be prone to excessive leaching following moderate to high rainfall events. Conversely, herbicides with low solubility may struggle to provide good weed control if conditions are dry after application, since the low solubility means there'll be little herbicide available in the limited soil water. All pre-emergent herbicides need some soil water for both activation and incorporation. Dale Shaner explains.
The worst case scenario is if you have a real dry soil, but you have a moist barrier or moist soil underneath the dry soil where the weeds can germinate from. And under those circumstances, you'll find that the weeds will escape, especially things like metolachlor and dimethoxamide, because the herbicide isn't available, it's not really in the soil solution, and those weeds can emerge through the dry soil and not be exposed to the herbicide at all.
In addition to solubility, how tightly a herbicide binds to the soil and organic matter will influence where it moves through the soil profile. After incorporation into the soil by rainfall, cultivation or the planting operation, some herbicide will bind to the organic matter and soil particles. How much and how strongly it binds varies from herbicide to herbicide and is also influenced by soil type. The strength of binding is expressed as the soil water adsorption coefficient, or the herbicide's KD value. Typically, this KD value is adjusted for the organic matter content of the soil and then is reported as a KOC value. These K values reflect the ratio of herbicide absorbed into the soil or organic matter compared to the amount remaining in soil water. The Group B herbicides such as trisulfuron and chlorsulfuron have very weak binding, preferring to remain in the soil water phase. As a result, they are prone to leaching. By comparison, herbicides with high KOC values such as the Group D DNA herbicides, pendimethalin and trifluralin, bind very tightly to soil and organic matter and generally will not be moved by subsequent rainfall. They tend to stay where they are put. Group J herbicides such as triolate and prosulfocarb also bind reasonably strongly to soil and organic matter. S-metolachlor has moderate binding but relatively high solubility, so it can move down the profile following significant rainfall. Peroxasulfone is not strongly bound, however the solubility is quite low. This generally limits leaching unless rainfall is heavy. Binding is a chemical reaction with the soil and takes some time to occur after the herbicide has been incorporated into the moist soil. If the initial rainfall event after application is large, then most herbicides can be moved down the profile before binding has had a chance to occur. Potentially, this can move an otherwise stable herbicide into the seed zone, which can result in crop injury. This combination of solubility and binding also dictates how a herbicide will behave when applied to standing stubble. For example, a herbicide such as trifluralin that binds very tightly and has a very low solubility will bind tightly to stubble and not be washed off by rainfall. Therefore, herbicide landing on the stubble will not even reach the soil and is effectively unavailable for weed control. Conversely, a herbicide with low binding and high solubility, such as chlorsulfuron, will be easily washed off the stubble with subsequent rainfall. In summary, it's important to ensure that when applying a pre-emergent herbicide that uniform coverage of the soil surface is achieved. Once the herbicide's been incorporated into the soil by rainfall, cultivation or the planting operation, how the herbicide's likely to behave will be dictated by the amount and timing of subsequent rainfall, the soil type, water solubility, and strength that the herbicide binds to soil and organic matter. Herbicides with high binding and lower solubility will generally tend to stay near the soil surface and will usually require good soil moisture at application and throughout the period of required weed control. Herbicides with weak binding and high solubility will easily move into the soil following rainfall, but may be leached down the profile with continuing rainfall events. How planter design affects soil and herbicide movement, incorporation, volatilization losses and the potential for crop damage is the subject of the second video in this series. If you'd like to learn more about pre-emergent herbicides and their behaviour in the soil, GRDC's publication Soil Behaviour of Pre-Emergent Herbicides in Australian Farming Systems, a reference manual for agronomic advisors, is an excellent read and available online at the GRDC.